In the last section, you have learned how to predict patterns in historic data using classification algorithms. Now we'll dig more into clustering, which we've already introduced in a previous section. We'll start with hierarchical clustering, then switch over to distribution-based clustering, and finish with density-based clustering by introducing the dbScan algorithm. In this video, we introduce hierarchical clustering. We'll start with a recap of clustering, since we've covered that topic already in a previous section of the course. Then we'll introduce hierarchical clustering. This algorithm not only finds optimal point assignments to clusters, but tries this for different number of clusters in multiple iterations and set the clusters that are found from each iteration into a relationship. This algorithm not only finds optimal point assignments to clusters, but tries this for different number of clusters in multiple iterations and sets the clusters that are found from each iteration into a relationship. We'll see how this works and how we can make use of this additional information. It's hard to find out which rows are close to each other from a value point of view. When plotting the data, it is obvious that there are 3 clusters in the dataset, basically points belonging somehow together. Now, we could infer or even computationally calculate the center of gravity of each of those clusters and then manually assign each point to one of those cluster centers, also called cluster centroids. But of course, this is not something that we want to do manually. And anyways, this doesn't work anymore when analyzing data with more than 3 dimensions or columns respectively. We've already learned how to analyze this dataset with k-means, but now let's see how hierarchical clustering works and what benefits it brings along. As the name suggests, hierarchical clustering sets different iterations of the algorithm using a different number of clusters into relation. The bottom-up approach starts with n clusters. In other words, it starts with as many clusters as the data points in the dataset. Of course, this leads to an optimal assignment of each point to a cluster centroid, since every point is the cluster centroid of itself. Unfortunately, we won't gain any insights from just having n clusters. Therefore, we continuously merge neighboring data points into a lesser number of clusters until we've reached the point that there is only one cluster left containing all the points. The other way around, we could also use the top-down approach, which is significantly faster in computation. Therefore, we start with a single cluster containing all points and divide it such that the new assignment of points to clusters lead to a minimum sum of distances between all points to the new cluster centroids. We continue until we reach a state that every point forms a cluster centroid of itself. As in k-means, distance between points and between points and cluster centroids has to be measured continuously here as well. Hierarchical clustering can make use of different distance measures. You don't have to understand those in detail. The only thing to remember is that Euclidean distance is the default for most applications and that using a different distance measure can lead to a different distribution of cluster centroids and to different assignments of points to clusters. Additionally, please be aware of the fact that Euclidean distance tends to work worse on higher dimensional data. Therefore, when analyzing such data, you are forced to experiment with other distance measures. Again, this choice comes from experience, since it is hard to impossible to choose it algorithmically. But wait, one important part of the algorithm we haven't covered so far. How does the hierarchical clustering algorithm know which clusters to merge or split in each iteration? Therefore, a linkage criterion is used. Let's have a look at the most easy one. We just measure the distance of all cluster centroids to each other and merge the ones with the lowest distance. But there exists a variety of other linkage criteria, and again, choosing the correct one depends on your data and an optimal choice is made by experience. So independently whether we choose the top-down or bottom-up approach, we end up in a diagram like this. On the top, we see every point assigned to an individual cluster. On the bottom, we see all points assigned to one individual cluster. And in between, we see the situation for a different number of clusters between n and 1. But now, in addition to that, we see also the relationship between all the assignments of points to clusters. And this is a particular strength of hierarchical clustering, especially if there are hidden relationships between clusters, like in phylogenetic trees, for example. So after a recap on clustering, you've now learned how hierarchical clustering works, our first algorithm which doesn't need an initial guess for potential number of clusters in the dataset.